So next I'm going to talk about latent diffusion models. If you, for example, have heard of stable diffusion, that is based on latent diffusion models. So what is the problem that we want to address here? So the problem is that images are high resolution in many cases. So you have perhaps many pixels, 1024 by 1024, more than a million pixels. And in the generation, if, for example, you consider DDPM, or even during the training, so you are working with really huge vectors, like vectors of millions of numbers. That is not scalable. It is very difficult to train these models. It is quite difficult to produce high resolution images in a quick fashion. So that's the problem. So what is the solution here? I'm going to give you a hint. The solution is to use an encoder decoder. Compress your input to a smaller dimensional space. Do your diffusion in that space, in the latent space, and decompress it. Encoder, decoder. That is it. Okay, so here's the idea. So here's your input. You have an encoder. Map it to a smaller space. Okay, so now you have a more manageable vector, right? So if you even think about like a 2D version of it, if your X was 1024 by 1024, maybe your compressed version is only 32 by 32. Much smaller, right? You have now about like 1,000 numbers to work with. Before, like you had 1,000,000 numbers. 1,000 reduction in terms of the space and the dimensionality of your input. Okay, so do whatever you want to do in this space. This is the diffusion process. Go towards noise. This is the normal. And then again, for the reverse, start with the noise, bring it back, right? So basically, this is what we have already covered. You really didn't say, your inputs are images or whatsoever, right? It could be any distribution. It could be the distribution of the encoded version of your images. Doesn't really matter. And then for your output, don't display this. Use a decoder, and then have this output. Let's call it XM. That is the whole idea of latent diffusion models. Maybe I should have called it latent diffusion models in moment. All right, so what is the, you obviously have different choices to use for your encoder and decoder. In the original paper, they're using something very similar to VQ GAN. And I want to emphasize, this is fixed. You are not optimizing this. You take an off-the-shelf encoder and decoder. That's it. You could use any other encoders. But the one that we are using is based on VQ GAN. And let me, on a side note, just explain how VQ GAN is trained, just for you to get a little bit of a feeling. It's a pretty decent encoder and decoder. It's based on quantization in the latent space. It's a side note, right? So the way that this encoder and decoder, again, this is trained separately. You are not training during your diffusion. It's trained in another time, and then you're using it as a fixed encoder and decoder during the training of your diffusion. But I'm explaining how it was previously trained. Okay, so you have an input X, They use a CNN encoder. And you get basically a latent representation. I'm going to show it in 2D. And they quantize this latent representation. You have like a quantization numbers here. Each code or each number here corresponds to a code or a vector in your code book. Let's say number 1 corresponds to these numbers. Number 2 corresponds to these numbers. And you use, again, a decoder, a CNN decoder, to decode. It is very similar to the quantized variational autoencoder that we already talked. You can look at the reconstruction loss as L2 loss. The quantization is not differentiable. How do we manage that in our integration, in our gradient computation? We just ignore it, right? And what do we call it? It's straight through estimators. Okay, fantastic, good. But they, instead of the L2, they use LPIPS distance between X and X tilde, X hat, between input and output. LPIPS is a very interesting distance. I won't go into the details, but again, it is defined based on features of a normalized feature of a convolution network. So you get like these, basically map your X to the features, the normalized features, and then look at the L2 distance in the feature space. But again, it is a distance. It's a very useful distance, especially in terms of capturing the perceptual changes between your between the two inputs. But they also add a discriminator, patchwise discriminator. Patchwise discriminator to ensure the patches are photorealistic. So for each patch, they ensure that the quality of it is good by just by just training a discriminator. Look at different patches, it goes through a discriminator. And it is kind of similar to what we covered in the GAN lecture in terms of ensuring the distribution of the patches across your inputs. Roughly speaking, they are similar to each other. So that's why the name GAN comes from. And this is quantization is because of the codes that they consider. So that's it. That's the latent diffusion models. Easy. Okay, so we have time for one question. Yes? Speed. Instead of working with million numbers, you work with 1,000 numbers. Because you're, with quantization. So I thought, so it just, in terms of the quality of the encoder and decoder, empirically it improves the quality. And it is because you are basically putting a little bit of a structure in your latent space. So the small variations don't change your latent code. Yeah. I thought about like, what you asked about like the encoder and decoder. Okay. So the next topic that I want to cover is conditional image generation. So far, we talked about generative models in a broad sense, meaning that you have some training examples, let's say photos of cats or dogs and other types of photos, and you want to train a model to be able to produce photos and images similar to examples that you have in your training. But in many practical cases, you may want to have some additional control. In addition to saying that, okay, I want to generate some realistic photos of cats and dogs or other scenes, I want to condition it on a particular input. Maybe that input can be text because text is easy for describing some of these conditions. So how can we think about text to image generation? Obviously, you have seen many such examples of those models that with text, they can generate photorealistic outputs, even videos. So you can have text, you can generate videos. So what is the underlying idea? How can we bring text into the picture here? So the main technique is using cross attention. We discussed it in the lecture that we talked about transformers. So my battery is dying, so hold on a second. See what happened. Oh, no, we have carefully charged. Okay. So we are going to use cross attention. Let's look at the latent diffusion model. Okay, so we have X as we pass it through our encoder. And then obviously we get a decoded version of it here. And here we do forward process. We go towards noise. And here we do the reverse process. We go up until we reach ZT. Let's call these Z's. Then we work in the latent space. Then this will be Z0, the noiseless latent code. When T is large, this will be, roughly speaking, normal. Again, we sample from ZT, which is normal in the reverse direction until we get an estimate for here. And then we recover the original input after applying the decoder. Okay? And at each step of the process, we are applying basically a denoiser, right? That was the formulation that we saw last time. So at each step, we are going to apply a denoising network. In most practical implementation, not all of them, people use UNet as the network architecture for your denoiser. That's the UNet that we are using here. So again, in the UNet, it is decreasing the dimensionality and then it increases the dimensionality. That's the forward and reverse processes that we have in diffusion models. In latent diffusion, we just do that in the latent space. That's all. I'm just reviewing what we have covered so far. But now, what happens if I have text? So if I have some text, for example, a dog running, I don't know, next to a river. So it's a text, or whatever scene that you want to describe. I'm going to pass it through a text encoder. So I'm going to have like these tokens for my text. It can be a transformer. It is a transformer. And then I'm going to have a cross attention between the output of my text encoder. This is not trained. This is fixed. I can pick whatever text encoder that I like. I'm going to have a cross attention between the output of my text encoder and the layers of my unit. So let me see how I can. Let's consider one layer. I'm going to have a cross attention. I'm injecting my text somehow into these layers. I'll explain how we can do that. Attention. Okay. So let's look at one layer at my unit and the output of my text. Let's see how I can inject my text into that layer, because that's the goal, right? As a cross attention. So here's the text encoder. I'm just drawing it separately. Text encoder. These are my input text tokens. I'll get some output tokens. This is going to provide keys and values for me. So just to recap from the transformer lecture, so every token evolves in your layers. Right? When you have like attention, you apply some projection matrix to that vector, to individual vectors. For each token, you compute 3 vectors: keys, values, and queries. And for self-attention, then you look at the similarities between keys and queries, and then you combine values based on that. So here, from the text side, I compute keys and values. Let's consider a particular layer at my unit. And let's look at, let's say, one particular query here. Let's call it Q1. Okay, so I'm going to compute the similarity of this vector, the query vector from my unit feature, with each of these keys from the different tokens of my text. Basically, I want to see this particular feature at this layer of my unit, what kind of text information it has in it. So that's basically the similarity. I compute the inner product. I compute these weights, let's say this P11, P12 to P13 in this case. And then instead of using the value that I get for that feature in that layer of unit, I'm just going to replace it with the values that I get from the text side. So I'm going to replace this, and I'm going to say, okay, look, the output will be the sum P11 times V1, the value that I get, because I know this feature has P11 similarity with this key coupled with the value from the text side. So I'm injecting text into my unit layers up until, let's say, P1, I don't know, n times Vn. So I update the output vector for that particular token, for that particular feature at unit, using the values of my text encoder, but the way I don't know like which text, which word corresponds to which feature, right? That's the similarity between queries and keys. I say, okay, this feature looks like maybe like the K1 corresponds to cat. Maybe this probability is close to 0.9. Then I'm replacing the value for cat for that particular output. I'm injecting in a soft manner, in a cross-attention manner, the text information into my units. That's called cross-attention. In fact, there are different designs of it, but different. It is not done in just one layer. There are like, if I remember, 4 layers in stable diffusion. They have cross-attention. So that if don't quote me on that, but if that's from my memory, you have 4 different layers of cross-attention. At different layers, you inject information from your text. And that is it. That is state of the art. If you see all of the amazing image and video generations based on text, that is it. Obviously, you can play with it. You can make some variations, but that is how conditioning works in the context of generation. Everything remains the same. The way that we are training, the only thing is that we are injecting some information from the text side to the unit. Okay, so let me pause here. We have time for one question because I want to cover one last module before the wrap of diffusion. Right? So I think we are really covering a lot of ground. Yes.
Is Q the weights of that layer or the output layer?
No, it is the. Let's say you are looking at patches or tokens. Q is the application of like a projection matrix to the representation for that particular node, for that particular token. That's the query vector. All right, so we have 5 minutes. I want to cover one more topic before finally wrapping up. So the final topic is control. So in some cases, in addition to text, you may have like some additional guidance for your diffusion models. So we argued how text can be inserted, and it is because of like the nature of the text, right? So you're again using transformer, you have like these queries and values, then you can use cross attention. But what if you have, let's say, an additional information like a sketch? Let's say you're drawing a sketch of an image. It's my tree, and I want to generate a realistic version of this with the exact location of a tree here. Maybe I have like maybe a cloud here, maybe sun is here, maybe there's a river here. There's a sketch. I want to generate a photorealistic version of it. It's an additional guidance. How can I, again, inject this information? How can I help my diffusion model to be able to generate such outputs? Okay. So the idea is simple. It is introduced in a paper called Control Net. Okay, suppose you have a neural network. Any neural network, it has an input, it has an output, right? X, Y. You can imagine, these can be different, layers or whatever process that you're doing. So you have an input, you have an output. Okay, and I want to somehow change my Y with some additional context, with some additional information. Right? So how can I do that? So here's the proposal. It says, okay, let's just start with the input that you have. That's C, that's your conditioning. It can be the sketch that you have. It can be some other information. But let's assume you have C, roughly speaking, the same size of your X. Maybe a sketch of an image for now. So they apply a zero convolution to it. What is a zero convolution? It is I would say it is not a very great name. By zero convolution, it's just a convolution operation, but they start with all zeros, because they don't want to have any values at initialization. When it is zeros, then basically you don't have anything. It's not a great name, I have to say. So in fact, this convolution is a 1-by-1 convolution. What is, again, 1-by-1 convolution? It is just a matrix product. Side note, let's say you have an image X with, let's say, 3 channels for now. So at every point, you have a vector of length 3, right? Because you have 3 channels. A 1-by-1 convolution just takes this vector and multiplies it with a matrix. That's it. You do it for every location. That's called 1-by-1 convolution, or folks like me can call it matrix multiplication. Okay, again, that's a simple operation. It's adding some flexibility to it. Okay, so we are going to add X here, and we are going to have a trainable copy of the network here. So this is copied here, exactly the same weights, and have an additional 0 convolution here in the output, and then add the output to your original output. So this part is not going to be trained. This is locked. Not going to be trained. Frozen. Okay, so let's see what happens. At the beginning, your 0 convolution, it's basically 0 initialization, right? So this C is multiplied by 0. Nothing is happening. So you get X here. It's a trainable copy. It's exactly the same neural network that you had before. Again, you have like very close output as Y, but again, you multiply with 0, then you get 0 here. So your output is like basically Y at the beginning. And then you can train this part to somehow inject, again, in a heuristic fashion, the information of your conditioning into your Y. So you massage it a little bit. These are like trainable weights for your convolution. You change this part. Again, that information is somehow added to your output. So, but the good thing is that here, the neural network, the original neural network, doesn't need to be trained. So this is frozen. So that helps quite a bit. So the learning, again, done in a similar fashion. You can even add text conditioning to it. You minimize over your parameters, expectation over noise, and your denoiser here not only have the noisy image, the time, the conditioning on text, but also has some other additional conditioning that you have here. It's a task-specific conditioning. And this is text. And this is the noisy image. All right, so this conditioning, similar to cross attention, right? So for the text, we use cross attention to somehow inject the text information into the unit. You can plug this into different parts of your unit to inject, again, some information, additional information that you have for some of the samples. Right? So you need like input and output samples to train. You may say, okay, so these are some sketches, these are like some corresponding outputs. So I can train my control net based on this. So in the test time, when I have the control, then I generate samples that follow the conditioning that we have. Okay. Any questions? Oh, here, yes. It's a design choice. Okay, so yes, like for example, this topic is like so recent, right? So these methods are developing, last couple of months or so. but I just wanted to show you how if you see like, okay, I have a sketch and now all of a sudden I generate a realistic, image. That is it. Right? So you know different components of it. So it is, as you can see, many of them are design choices. You can think about like better ways of injecting such information perhaps into your generation process. Now that you have hopefully a good understanding of the foundations of these models. That is all for diffusion models. Thank you. We'll cover other topics next